Okay, let's dive right in. We all kind of know about fermentation, right? You see it in things like bread and beer, but what happens when you take that process and you blow it up to a massive industrial scale? We're going to take a peek inside these incredible high-tech kitchens where microbes are the real star chefs.
So here's the central question, and it's a really cool one. How in the world do we convince these microscopic organisms, our tiny little chefs, to cook up the exact products we need on our schedule and to our precise specifications?
And I mean, we are not talking about a small homebrew here. The goal is to produce literally tons of stuff. Everything from the enzymes in your laundry detergent to biofuels to life-saving medicines like insulin. The scale is just, it's kind of hard to wrap your head around.
Well, the answer lies in these massive, gleaming stainless steel tanks. They're called bioreactors. You can just think of them as the ultimate, perfectly controlled, high-tech kitchens for our microbial workforce.
So how do you actually do this on an industrial scale? It's definitely not as simple as just leaving something in a jar and hoping for the best. No, this is a highly sophisticated scientific process, and it's all designed for maximum efficiency.
At its heart, what we're really talking about with industrial fermentation is harnessing the natural metabolic power of microorganisms. We're essentially giving them a job. Here are some cheap raw materials. Now eat them, and please transform them into something way more valuable. And, any great dish starts with the right ingredients. For our tiny chefs, that's the culture medium. It's a perfectly balanced liquid diet, a gourmet meal for microbes. And get this, to keep costs down, it's often made from inexpensive industrial byproducts, stuff like molasses or whey. All right, so let's pull back the curtain and step inside the industrial kitchen itself. The bioreactor. You're going to see how this thing is an absolute masterpiece of engineering that ensures a perfect batch every single time.
First up, you've got the impeller. This is basically a giant, super powerful whisk, and it's constantly stirring the mixture. This is absolutely critical to keep everything perfectly mixed up so that every single microbe has access to all the nutrients it needs.
Next is the sparger. Think of it like a high-tech aerator in a fish tank, but way, way more intense. It pumps sterile air in from the bottom, creating these bubbles that rise through the liquid. For a lot of these microbes, oxygen is, well, air. They need it to work, so this constant supply is essential. And this is where you really see the insane level of control that's needed. All of that microbial activity, it generates a ton of heat, enough to literally cook the very organisms we're trying to grow. So, to stop that from happening, a cooling jacket wraps around the tank, acting like a giant refrigerator to keep the temperature just right. And all these sensors for temperature, pH, and oxygen, they're really the eyes and ears of the kitchen. They feed data to a control system that automatically makes tiny little adjustments, keeping our microbial chefs perfectly happy and super productive in their custom-made environment. Now, what's really fascinating here is that just like in a real kitchen, there isn't just one recipe. There's not just one way to do things. The method you choose depends completely on what you're making and how the particular microbes you're using like to behave. For example, you could do a batch process, super simple, put everything in at once, let it cook, and harvest at the very end. Or you could try a fed batch, where you add more nutrients over time, which can seriously improve your yield. And then there's a continuous process, which is like a nonstop production line, constantly feeding in raw materials and harvesting the product. The chefs can also work in different kinds of kitchens. Liquid fermentation is basically like making a giant soup, and it's perfect for things like bacteria and yeast. But some microbes, especially fungi, they don't want to swim. They prefer to grow on a damp, solid surface, which is a lot closer to how they live in nature. Each method has its own clear advantages. And yeah, the visual difference is pretty stark. On the left, you see that gleaming steel vat for liquid culture, and on the right, microbes growing on a solid material, something like agricultural waste. It really shows you how the kitchen has to be totally redesigned depending on the chef and the dish you want to make. Okay, so in any kitchen, hygiene is critical, but in a microbial kitchen, a single invading microbe, just one unwanted guest, can ruin the entire multi-thousand-liter batch. The stakes are just incredibly high. A contamination event is a total disaster. The invading microbes can outcompete your chefs for food, they can produce toxins that kill them, or they might even break down the very product you're trying to create. It can bring the entire multi-million-dollar process to a grinding halt. So how do you prevent this?
you go to war on germs. Before anything even starts, the entire kitchen, the tank, the pipes, the nutrient medium is completely sterilized. This is often done with intense, high-pressure steam, basically pressure cooking the entire system to kill any and all unwanted microbial invaders.
But what about things that can't take the heat, like certain vitamins or even the air supply itself? For those, you use these ultrafine filters. You can think of them as microscopic bouncers at the door, physically blocking any contaminants from getting into the sterile party. Okay, so the cooking's done, the microbes have made what we want, so now what? How do we separate the dish we want from the tiny chefs themselves and all the leftover ingredients? This next phase has a name. It's called downstream processing. And honestly, it can be the most complex and expensive part of the whole shebang. It's a three-step journey. First, separation, then purification, and finally, formulation to get the product ready for the world. The first step is usually a simple mechanical separation. Machines like this industrial filter press work on the same basic idea as a coffee filter, just on a ridiculously massive scale. It squeezes the liquid broth away from the solid mass of microbial cells. From there, it's pretty much pure chemistry. You'll use techniques like solvent extraction or crystallization and spray drying to isolate, concentrate, and stabilize the product into its final pure form. This is basically the plating stage, getting it ready to be served. I mean, it's pretty incredible when you think about it. We've learned to manage these microscopic factories with such amazing precision, creating everything from sustainable fuels to brand new medicines. So the truly exciting question is this: what new ingredients are we going to ask our tiny chefs to create for us next?